Let's work on number 4 from the 2015 AP Calculus AB free response questions. We're going to consider that differential equation. And when you look at it, your first thought might be, well, let's separate the variables and let's stop. They didn't ask us to do that, and they actually won't. And the reason they won't is because you can't separate the variables using the conventional methods that we've been doing. So you can't add this y and move it over and then move the dx. And you can't separate the x and the y. It's not going to work. But clearly, they're asking us to do a slope field. So on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. There are going to be 2 points, like scoring points, available for this question. And just so I don't write on that copy, I have made this that looks much worse. Anyway, I'll go through this part very quickly. This coordinate is 0, 1, so we plug in, well, a 0 and a 1. And when we plug in a 0 and a 1, we get -1. There we go. This is 1, 1, and that gives us +1. This is the coordinate 1, 2, obviously. That gives us a 0. And this one is a -2. This one is a +1. Oops, kind of went astray there. And this one is a +3. And there we go. And just in case you need to know, whenever they are grading this particular one, they would give you a point where the slopes equal 0 and a point where the slopes equal 1. So there's a point for that one and a point for that one. What about these guys? I don't know. They don't always grade the slope field problems consistently. But just get it right. You won't have to worry about it. So that was part A. So let's move on to part B. And part B said find d squared y over dx squared. Okay, that's the notation for the second derivative using the dx stuff. In terms of x and y, we'll just stop right there. Let's find that. So before we read any further, let's just go ahead and do that. So we have this, and we're going to take the derivative of it again. So when we take the derivative, implicit differentiation, the derivative of the derivative is, well, the second derivative, and that's what they asked us to find. The derivative of 2x is 2. The derivative of 1y is 1, technically -1, but it is 1y dy dx. And if you stop here, then you've really cut yourself short because you know what dy over dx is. It's this. So this is really 2 minus 2x minus y. So let's go one more step. This is going to come in handy later. Trust me. There we go. We have just found the second derivative. So for what it matters, that is worth 1 point right there. So we have just earned a point. But now let's finish answering the actual question. Again, if you've seen another video that corresponds with this, you kind of realize what I'd done earlier in another problem. If there is a part, like part B here, that asks you to do 2 things, you can do one of them and easily move on and forget the other. So be careful. Anyway, determine the concavity of, concavity, second derivative, of all solution curves. What does that mean? Okay, so if I was to sketch this entire thing, I could draw like solution curves through it depending on what the C value is if I truly could separate these and integrate them. So I'd draw this. You'll see a better visual for it when we get to part D. Okay, determine the concavity of all the solution curves for the differential equation in quadrant 2. Okay, well, quadrant 2 is over here, just doodling here. So here's quadrant 2. And give a reason for your answer. So here goes. I'm just going to start kind of talking my way through it and writing down what is going through my head, which actually might turn into my answer. Okay, let's talk about what quadrant 2 is. Well, quadrant 2 is a location where all the x's are negative and all the y's are positive. So we could say it's negative comma positive there, right? So in quadrant 2, all x values are negative and all y values are positive. Okay, now they asked me to talk about what that really means in terms of concavity, so I need to deal with this second derivative. So I'm just going to continue my little stream of consciousness here, but here's my second derivative. Let's think about it though. I have 2 minus 2 times a negative. X is always negative, right? So 2 minus 2 times a negative. So this is so far 2 plus something, because that becomes positive, and then plus something that's always positive. So we have 2 plus something plus something. We're always going to get a positive. Therefore, and stream of consciousness here, but this is working. Therefore, my second derivative I'm going to be kind of specific here, which is 2 minus 2x plus y is always greater than 0. So let's finish answering the question. All solution curves are concave up. There we go. And that actually is the answer. And in terms of what they're looking for, they gave you a point for that. And they would also give you a point for this with that reason right there. All right, let's move on to part C. And part C said, let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. Okay, now your first thought might be what my first thought probably was, and that happens a lot with these. And again, you might go back to, well, then let's separate the y and let's bring the dx. No, you can't. Often you can. This time you can't because they're separate terms. And you may want to find out what the c value is by using coordinate 2, 3. Well, you can't, okay? Does f have a relative minimum, a relative maximum, or neither at x equals 2? I can't go back to the original function, but I can talk about minimums, maximums, or neither. All right, minimums and maximums occur where the derivative equals 0, right? This is the derivative. They gave me the derivative. So what I want to do is see if the derivative truly equals 0, and then I'll be able to go even further and say it's a maximum or minimum based on second derivative stuff, which I will talk about in a minute. So here goes. First thing I'm going to do is just decide if the derivative equals 0. Now, I could say, well, or the derivative doesn't exist. Well, this is going to exist, okay? It's going to exist everywhere. You never divide it by 0. There's never any craziness like that, okay? So I'm going to check and see what happens at 2, 3. So I'm going to use kind of a weird notation. Let me show you what it looks like on the answer key. It's this little guy right here, but we've seen it before. Okay, so let me slide that out of the way and show you. I'm going to evaluate the value of the derivative at the coordinate 2, 3. And you've seen this before, and I'm just kind of showing you a little more specific notation. Don't panic if you don't write that. You could write in words. The value of the derivative at 2, 3 is, I'm just showing you this. And you've actually seen that vertical bar before when you were doing the fundamental theorem of calculus. You'd be like, well, I'll evaluate it from here to here. It's that kind of thing. So equals, well, 2 times 2 minus 3. And so that's equal to 1. All right, let's not lose sight of what we're doing. Does it have a minimum or a maximum? Well, it would have a minimum or a maximum if the derivative equals 0. The derivative doesn't equal 0. I'm going to write that down just because I really want to tell them that I understand. It is very helpful to clarify your understanding as you write these down. So what if it equals 1? Did they know that you were actually looking for a 0? Tell them. Tell them by writing that. Because this is not equal to 0, the value of the derivative at 2, 3 does not equal 0, and you can write it in mathematical notation if you want, does not equal 0. F of x has neither a max or a min at that point. We're explaining our thinking in words. Okay, now I'm going to digress for just a second here. I'm going to grab a random scrap piece of paper, and I'm going to talk about briefly what would happen if this did equal 0. Okay, so if this did equal 0, let's pretend like 2 times 2. Don't write this down. It's so mathematically wrong. If for some odd reason that is correct, and it's not, but if it was, right? Let's actually fix it to where it will work. Let me change the actual problem. Let's suppose part C said, find out what happens at 2, 4. And is it a maximum or a minimum? Max, min, neither... that kind of thing. If that was the actual problem, then we would find this, instead of me giving you something mathematically incorrect, right? Then we would evaluate this at 2, 4, and that would give me 2 times 2 minus 4, which would be equal to 0. And at this point, I would say, oh, wait. The actual derivative does equal 0. So now I need to go further and actually answer the question and say, well, maybe it's a minimum, maybe it's a maximum. It's not neither, or, well, it might be actually, but we'll deal with that in a second. But I have figured out that the derivative equals 0, so I can go further. Well, here goes. Let me grab a random piece of paper. No, let's not. Let's grab a ruler. If it's concave down, we've been through this, but if it's concave down, then if you know that this coordinate right here, up at the top, is where the derivative equals 0 and everything around it is concave down, then it is a maximum. If you have concave up and you know that that coordinate, which happens to be the bottom, is where the derivative equals 0, then you have a minimum. So once I have this, I didn't in what they asked me, but if I did, then I would go further and I would find the value of the second derivative at that point, at 2, 4. And the value of the second derivative is something we've already found, so I'm going to go 2 minus 2 times 2 plus 4, and that gives me 2. And so the answer to this question would be, and I'm going to draw my thinking first. This is concave up. Because it's concave up and the derivative equals 0 there, I have a minimum, right? Okay, so if the problem would have said blah, 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 2, 4, then I would do this. I'd get a 0 and I would proceed and keep on moving. And I would say 2, 4 is a minimum since dy dx at 2, 4 equals 0, and the second derivative at the coordinate 2, 4 is positive, so it's concave up. And we've really answered the question just by saying that. Okay, again, not what they asked. I just wanted to go further because I felt like when I did this problem and I did part C, I was a little disappointed. I was like, oh, well, man, it's not even equal to 0, so it's neither. Dull. How completely dull. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. We have encountered one like this in class, and after much studying, I am prepared to give you an explanation that really requires a lot of mathematical doodling, which might seem a little frustrating. So I'm going to read the problem again, and I'm just going to write stuff. When you don't know what to do, let me give you 2 hints. If you don't know what to do and you know it's going to waste your time, move on. It's very easy to just cut your losses and move on. And move on to one that you can get points for. However, if you have time, I recommend that you begin to write down what you know, and things might begin to come together. All right? And that's exactly what we're going to do on this one. So find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Now, I want to kind of, well, at the end, I'll show you something. I want to show you the visual for what this really looks like in the context of this entire thing right here. Okay, so what do I know? Well, I know that. And now in a minute, I'm going to, just after I've written down everything I know, I'm going to start doing stuff to it. So I know this. dy over dx is equal to 2x minus y. What else have I found out? Well, I found out the second derivative, and that was 2 minus 2x plus y. And you found out some other things too, like you found out what happened at the coordinate 2, 3. That's not really relevant for this. Let me write it if you need to, but it's not super relevant. Okay, so what can I do with this? Well, here goes. What's the slope of this line? M, right? This is a slope. Now, if nothing I'm saying is making sense, then I'm following a random line of thinking and hoping it will get me somewhere. So here's what I'm really going to do. I'm going to take the derivative of this. The derivative of y is dy dx. The derivative of mx is m. The derivative of b is 0 because it's a constant, right? Okay? So there we go. Maybe this will get me somewhere. So how about I just set m equals equal to that. Maybe this will work. Maybe it won't. Maybe it comes in handy. Maybe it doesn't. I don't know. But it's something else I know, and I'm just slowly beginning to, gain some traction. By the way, I'm going to go ahead and tell you, that's worth a point right there. You earned a point just by doodling. Lucky you. Actually, we earned another point right here. There we go. We just got 2 out of the 3 points that go along with this. By the way, I didn't give you the points for this one. That was worth a point, and then that explanation was a point. All right, let's move back to part D. Okay. I want to find the values of M and B for which this is the case. And this is where things get a little tricky. There are 3 points available on this part. You've just earned 2 of them. So lucky you. Just by doodling, just by like saying, hey, how about I try this? So here goes. Here's what I'm going to do even further. If I took the second derivative of this, what would I get? This may or may not go through your mind, but don't worry. The derivative of m, well, m's a constant, so it's 0. And when I first saw this explanation, it started to click for me. And it happens just by experimenting. The second derivative is 0. Well, the second derivative is that. So 0 equals that. I hope you see what's about to happen. The problem said find the values of m and b. I can find it very easily. Let's solve this thing for y. Y equals, we'll move that over, it becomes 2x. We move that over, it becomes negative 2. And there we go. So m equals 2, b equals negative 2. Whoa, that just jumped out of nowhere. By the way, this is worth another point right here. There's your final answer. Found the values of m and b. All right, let's put this in context and make sure you understand it. When I saw a visual for it, then I began to understand it a little bit better. Clearly, you will not have this capacity on your AP test, but this is the slope field with the glare of my ceiling fan right in the corner. There it is. Actually, let me turn that light off. There we go. Here is the slope field that corresponds with this problem. And it goes from negative 10 to 10 on the x, negative 10 to 10 on the y. Okay, so again, you don't have that capacity on your AP test, but I want to give you a visual for it. So to really answer the question, and again, the question was, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation, meaning there's a line that goes through this. What is that line? So if I had this whole thing, where would I draw my line and it actually logically fit? Well, I could sort of, follow some of these curves here. By the way, that's why it's concave up in quadrant 2. You kind of go down and then you go pretty sharply till you get down to about here and it goes like that. But basically, there is what's called a slant asymptote, and it's very subtle, but it's right there. There it is. Now, maybe you visualized it and maybe you don't. But when I saw this whole thing come together, the problem started to make more sense for me. Let me show you this. If I put y equals, what was it, 2x minus 2? Yeah, 2x minus 2. Then enter. There it goes, right there. And that line goes through there, and it's a perfect fit. And everything above this line seems to be, and I don't want to speak in a way that's not correct mathematically, but it seems to be concave up. And everything below this line seems to be concave down. It's kind of like beginning to bend, kind of like this a little bit. So sort of bending downward. Maybe you visualize it and maybe you don't. But here's the point. At this place of the shift in concavity, we go back to the problem. There we go. At this point of the shift in concavity, I needed the second derivative. And again, maybe that didn't go through your head, but continuing to doodle and set these things equal to each other, it gave us our answer.